And in my opinion, the computer is the coolest invention humans have ever made. I spent the last several months building this very simple computer, which should allow me to explain the fundamentals of how a computer works. If you have not watched my other videos, this may seem complicated, but if you break it down into individual sections, it becomes quite simple. Understanding these fundamentals of electronics will be important, because after this we are going to build artificial neurons and non-biological life, as we work towards creating non-biological human consciousness. Everyone should know how to build a computer at the transistor level, so please share this video. The computer is powered with a 5-volt, 2-amp battery pack. If we look at the multimeter, we can see it uses just over 1 amp of current. It is built on 32 full-size breadboards and uses about 962 NPN transistors. The different circuits of the computer include the clock, program counter, ring counter, 10 bytes of memory, opcode register, opcode decoder, control matrix, data bus, accumulator register, output register, register B, and ALU. Let's run a quick example program and then talk about how each section of the computer is built. The program is going to load the A register with a value of 1, add 2, add 2, add 2, subtract 3, output the value of 4, and then halt the processor. First, the battery is connected to the computer. Connecting reset to ground on the data bus will clear the output register and set the counters to 1. Now the program is running. The first thing to notice is that the ring counter is incrementing 1 to 7. As the ring counter increments, it enables different circuits in the computer to send and receive data. For example, when the ring counter goes back to 1, it enables the program counter to increment. The 7 values of the program counter are connected to the first 7 bytes of memory. These 7 bytes of memory contain the 7 operational codes the computer is running. The opcode values are shown here and correspond to these memory locations. An example of the opcode being used is when the program counter has a value of 5. The 5th memory location will be used, which contains the opcode value 0011. When the ring counter has a value of 2, the opcode value will be placed onto the bus and latched into the opcode register. The opcode decoder will output 0100, which means this is the subtract command. When the ring counter goes to 4, the subtract value from memory location 10 is placed on the data bus and loaded into register B. Finally, when the ring counter goes to 5, the subtract circuit is enabled, the ALU is connected to the data bus, and the ALU output value of 7 minus 3, which is 4, is latched into the accumulator register. Now let's watch the entire program run from start to finish. Step 1. The value of 1 is loaded into the accumulator register. Step 2. Add is on the decoder, 2 is placed in register B, 1 plus 2 is 3. Step 3. Add is on the decoder, 2 is placed in register B, 3 plus 2 is 5. Step 4. Add is on the decoder, 2 is placed in register B, 5 plus 2 is 7. Step 5. Subtract is on the decoder, 3 is loaded into register B, 7 minus 3 is 4. Step 6. Output is on the decoder, the A register value is placed onto the bus, which gets latched into the output register. Step 7. Halt is on the decoder. The clock output is sent to ground when the ring counter hits 7. This halts the computer. The program is complete. Now let's talk about how each section of the computer is built. We will start with the clock. The clock is an astable multivibrator which is connected to the ring counter and data bus. Via the data bus, the clock also connects to these other circuits. Next, let's talk about the ring counter. The 7-stage ring counter is built with 7 edge-triggered JK flip-flops. The triggers for each flip-flop use a small capacitor. Here is a diagram showing one JK flip-flop, and here is a diagram showing how the flip-flops are connected. All of the flip-flops are connected to buffers to allow information to be sent to other circuits. The edge-triggered JK flip-flops could be built with master-slave JK flip-flops, but using the capacitor and resistor as a trigger makes it so significantly fewer transistors are needed. The program counter is also built with 7 edge-triggered JK flip-flops. It is common for the program counter to be a binary counter, which I showed in a previous video. However, it is easier to interface with our memory module using a second ring-style counter. This is because the memory module would have to decode the binary value to know which byte of memory to enable. The output of the memory module decoder would be very similar to the output the ring counter provides. If you want to know how a decoder works, this computer has a decoder for the opcode values. The 7 program counter values are connected to the first 7 bytes of memory, which contain the opcode instructions. Since the counter helps fetch the program instructions, it can be called the program counter. Let's discuss how the memory module is built. The values of the 10 bytes of memory are set before the program starts, and the values do not change. This is read-only memory. This module is actually simplified even for read-only memory, as each bit is a buffer that is hard-coded based on resistor connections to positive or ground. This makes it so only 2 transistors are needed per bit, rather than needing a data flip-flop and buffer for each bit, making the memory module much more compact. We would have needed 40 data flip-flops just to make 10 bytes of 4-bit memory. The buffers used in the memory module are simple tri-state buffers that invert the input. The buffers are active low, which means they are enabled when connected to ground. On the symbol, the 2 pins have a dot, bubble, or circle to show that an inverted signal is needed or is being output. The first 7 values contain the opcode instructions for the computer. The 8th byte has the value used for the load A command, the 9th byte contains the value for the add command, and the 10th byte has the value for the subtract command. Another part of the memory module is the tri-state buffers used to enable each byte of memory. This breadboard also has the display, which shows when a particular byte is being accessed. The input to enable each byte needs to be low, which is why these 7 inverters are needed. Each tri-state buffer is also connected to an open collector buffer in the control matrix to allow the tri-state buffers to be off when the memory module is not being used. If we were not trying to display when each byte is accessed, this could have been built in a simpler way. The opcode register is built with 4 master-slave data flip-flops. The opcode instruction that latches into this register is a binary number. This binary number is sent directly into the opcode decoder. The opcode decoder will decode each possible binary number into a single ON value, which can be used by the control matrix. The decoder is built with 5 3-input NAND gates. Since only 5 instructions are used, only the first 3 bits are decoded. The way the 3-input NAND gate decodes the number is fairly simple. When all of the inputs are on, the output of the NAND gate is off, which turns the inverter on, so the output for the circuit is on. There are also inverters before the NAND gate, which enable the inputs to the NAND gate to be on or off, depending which side of the inverter the input is connected to. For example, to decode 3, the output of the 3rd NAND gate needs to be off, so the output inverter will turn the output on. The NAND gate will turn off when all the inputs are on. This is done by connecting the first 2 inputs before the input inverters and the 3rd input to the output of the 3rd input inverter. This makes it so all of the inputs going to the 3rd NAND gate are on, which turns the output off, resulting in the output inverter turning the subtract command value on. The control matrix uses the opcode decoder and ring counter to determine when to enable circuits. Some circuits are enabled with a high signal, which is noted with a plus sign. Other circuits are enabled with a low signal, which is ground, and noted with a negative sign. Let's look at this circuit to explain how the control matrix works. When the opcode decoder has load A on, and the ring counter goes to 3, both inputs into the top NAND gate are on. This turns the top NAND gate off, which enables the load A value to be sent to the data bus from memory. Since the top NAND gate is off, it also turns the 3-input NAND gate on, which sends the load A register command. The result is that the A register latches in the load A value. Most of the other control matrix circuits work in a similar way. The data bus is a useful way for signals to be sent to and from each part of the computer. The 4 data lines of the data bus have pull-up resistors that connect to positive 5 volts. This makes it so that by default, all the data lines are on. When a circuit sends data to the data bus, it is actually providing the pull-up resistors a direct path to ground for any value that is off. If a value is on, the data line just stays on. This might seem counterintuitive, as it is common to think of a positive signal as being sent out. The other lines of the data bus include ground, positive 5 volts, the clock signal, and clear. The accumulator register is built with 4 master-slave data flip-flops. The top breadboard contains tri-state buffers, which allow the A register to send its current value to the data bus. Data is latched into the A register from the data bus when a load A command is sent from the control matrix. By having what is normally the clock input floating on, which means the clock input is always on, makes it so that the A register latches its value at the very end of a full clock cycle. This helps to ensure consistent latching behavior of the A register. The output of the A register is continuously being sent into the ALU. The B register is built with 4 data flip-flops. These are not master-slave data flip-flops or edge-triggered JK flip-flops. They are just regular data flip-flops. Each flip-flop input has a buffer. The clock gate, which is an AND gate, is enabled with a high clock signal and high load B command from the control matrix. When the clock gate is on, it latches the data from the data bus into register B. The latched data is then continuously being sent into the ALU. The ALU is built with 4 full adders, which allows the circuit to add 2 4-bit inputs. It also has 4 XOR subtract gates, which when enabled allows the ALU to compute A minus B. The bottom of the ALU contains tri-state buffers, which enables the ALU output value to be sent to the data bus. If you would like to learn more about how the ALU works, I do have 2 other videos about this. Finally, the output register uses 4 regular data flip-flops, just like register B. This register is very basic and simply latches the final value of the program and displays the result. The data bus value gets latched into the register when the clock gate receives a high clock signal and a high enable command from the control matrix. A cool thing about this computer is you can build it one section at a time. If you want to start building it, I would recommend starting with a 4-bit calculator that will turn into the ALU. Then build the clock, data bus, and accumulator register. If you can build those, you have a good understanding of how to build the entire computer. I drew the circuit diagram of the computer at the logic gate level. If you do not know how to build digital logic gates or flip-flops from individual transistors, I have in-depth videos about these topics. The only other person I know of in recent history that built a transistor computer on breadboards is Jerry Walker, and he wrote a book about it, which I would recommend. His computer was actually 8 bits. There are a lot of people that build computers on breadboards using integrated circuits. This is a quicker way to build a breadboard computer, but I like seeing exactly how each circuit is built by using individual transistors. This really helps understand the fundamentals. When building a computer this way, it is actually more thought-provoking than I anticipated, and it becomes clear that there are tons of ways to make improvements.